Hello, everyone. Welcome to the next lecture, lecture number 12. In this lecture, we're going to kind of finish this Laplace transform chapter. And in the next chapter, chapter number 13, we're going to talk in much more details only the circuits and how the Laplace transform is going to be used for the circuits. But we are kind of finishing up the general framework of Laplace transforms. And we also have started to see how it connects to circuits as well. But the next chapter is all about the circuits. Okay, so kind of some of the final thoughts and topics on the Laplace transform is I've divided this into like three parts. In the first part, we're going to talk about the poles and the zeros concept of the Laplace transform functions, f of s. And then in the other two parts, we're going to talk about a couple of theorems, initial and final value theorems. Okay, we're going to discuss that later. Okay, so let's get started. So in this part, right, so we have been evaluating this function from the circuit's time domain. We get a circuit's time domain function, we convert that into a Laplace domain f of s, right? And this f of s function may have some zeros in the poles. What do I mean by that? Let's see. And it has certain implications too. All right. So we have seen this equation in the past, right? This is a rational fraction, and whether it can be a proper or improper rational fraction depends on the powers of this s, right? If in the numerator, if your numerator has a higher power than the denominator, for example, if n is greater than m, you're going to get an improper rational fraction, right? Yeah, if n is larger than m, you're going to get an improper rational fraction. And how to solve that, we talked about this in we did a whole example problem. You start with the improper rational fraction, you do a kind of a long division, you convert that into a proper rational fraction, and then you apply your Laplace transform, and do the inverse transform as well. However, if you're going to have the values of the numerator n is less than m, then you're going to get a proper rational fractions, and we learned so many techniques on how to solve them depending on what sort of the roots we are expecting, right? We have real distinct roots, we have imaginary roots, we have repeated roots, etc., etc. So we also learned that how to convert these functions f of s into this kind of a form, kind of factored polynomials, right? And we did so many examples on how to convert these into factored polynomials. Now, when we convert them, both the numerators and the denominators into this form of factored polynomials, it starts to give us like something very interesting, right? So for example, in the numerator, I can see the roots of the s appearing, and in the denominator, I can see the roots of the s appearing, right? In the numerator, the roots are minus z1, minus z2, minus zn, s equals minus z1, s equals minus z2, s equals minus zn. And in the denominator, s equals minus b1, s equals minus b2, all the way to s equals minus bm are the roots of the denominator. So these roots practically represents the zeros and the poles, right? So let me write this down, and then I'm going to explain a little bit more what the zeros and the poles are, right? So zeros are roots of the numerator polynomial, right? And for example, the roots of the numerator polynomials are minus z1, minus z2, all the way to minus zn. Similarly, poles are the roots of the denominator polynomial. So you get minus p1, minus p2 to minus pn. And interestingly, I can plot these roots, both the zeros and the poles, in S domain, right? But I call it as S-plane. So we can convert this into an S-plane where the x-axis are the real values and the y-axis are the imaginary values, right? And we can plot these zeros and the poles, right? So for example, if z1 is minus 5, if first zero is minus 5, I'm going to plot it on the real one over here, right? So for example, if z1 is minus 5, I'm going to get 1, 2, 3, 4, 5. I can plot the 0 with a circle. Let's say if pole number 1 is minus 2 plus 2j, right? Which means that this is minus 2 and plus 2j is here, which is imaginary, 1, 2. So I can plot a pole with an x, right? Poles can be plotted with an x, so I can do -1, -2, plus 2j. I can plot. Okay, sorry. Don't make a 0 over here, just a simple cancel. So you can represent zeros with a 0 symbol and poles with a cross symbol, and don't put a circle on the cross, otherwise to avoid the confusion. I just did it out of habit. But yeah, this is how we can represent on the s-planes the zeros and the poles. So let's kind of do an example problem quickly and see how we can solve these for zeros and the poles and how we can plot them. Okay. So in this example, you have two functions, f1 of s and f2 of s, and the question asks you to find first the poles and the zeros. Again, these are your rational fractions, right? So first you're going to kind of factorize them, and then you have to find those roots and the poles, and then also plot these roots and the poles, right? So this is what we're going to do very quickly. Okay, so let's start with function number f1 of s, right? So f1 of s. The problem with f1 of s is, again, I want to get to this form so that I can easily see the roots or in the numerator and the roots of the denominator. But I have this form, right? So I need to get factored polynomials. So let's factorize the numerator, right? So I'm going to talk, let's numerator. Let's first play with the numerator, right? So our numerator is 40s cubed plus 440s squared plus 2200s plus 5000. The very first thing I'm going to do is I'm going to take 40 out and just write the whole thing, the rest of the thing down. Or why don't I write this thing down anyways? Equals 40 times s cubed plus 11s squared plus 55s plus 125, right? So this you can, the very first thing is to take the constant out, 40, so that your higher power has a one scalar constant with it, right? Now solve this cubic equation, right? Solve cubic equation. So once you're going to solve this cubic equation, s cubed plus 11s squared plus 55s plus 125, you're going to get s plus 5 as one of the factors and a quadratic equation of the factor because it's a cubic root. S squared plus 6s plus 25. Okay, and then solve the quadratic equation. Solve quadratic. So s squared plus 6x plus 25, right? So you can do s squared plus 6s plus 25 equals 0. And again, s equals to minus b plus minus b squared minus 4 times a is 1 and c is 2500 divided by 2. Okay, so once you get that, of course 36 minus 100 is minus 64, so you're gonna get imaginary roots. So your s is gonna come out to be as the 2 over here, the 2 roots of s over here is gonna come out to be minus 3 plus minus 4j, right? And then there's one root over here. So the 3 s roots are, so for example, the 3 factors that are going to come out to be s plus 5 times s plus 3 minus 4j and s plus 3 plus 4j, right? And the roots, all the 3 roots are, the one root is minus 5, the other root is minus 3 plus 4j, and the other one is minus 3 minus 4j. So these 3 roots are of the denominator, or sorry, are of the numerator, so they all represent zeros. So I'm going to plot them in a second. Okay, but let me start to compile the function, the new function as well, right? So I can write this top function as a 40 times s plus 5 times s plus 3 minus 4j s minus 3 s plus 3 plus 4j. Sorry, s is going to be plus 3 in both. Yes, over here. S plus 3 plus 4j. Okay, so this is the numerator. I'm going to do the denominator now. So denominator was this 4s square. I'm going to take 4 common and then do the whole thing again. So let's look at the denominator. Just forget about what is this. I'm going to show you this thing in a second. But let's solve the denominator first. The denominator. So the denominator is, you have, right, so this was the denominator. I'm going to take 4 out first from the denominator, right? So after I took 4 out, actually, why don't I write the whole thing first? So 4 times s4 plus 88s cubed plus 880s squared plus 4000s, right? Okay, and you can imagine it to be equals to 0. Okay, so the very first thing that I'm going to do is I'm going to take, since I have s common in all of them, right? If I were to solve this equation, the very first thing I'm going to do, I can even take s equals to 0 as one of the roots. So I'm going to take 4s out, and I will be left with s cubed plus 22s squared plus 220s plus 1000. Okay, now let's find the roots of cube, right? Solve cubic equation. So my cubic equation again is s cubed plus 22s squared plus 220s 1000 should be equals to, once I'm going to solve it, I'm going to get one factor as s plus 10 and one quadratic equation, s squared plus 12s plus 100. Okay, now I can also solve the quadratic equation, which is s squared plus 12s plus 100 equals 0. So s equals, again, minus b plus minus b squared minus 4 times a times c. 4 times a is 1 and c is 100, so 400 divided by 2. Okay, nice. So the two roots that I'm going to get over here is minus 6 plus minus 8j. So in total, I got 3 roots. One, s equals to 0. Another one is this one, s equals to minus 10. And the two other ones are over here. S equals minus 6 plus 8j. And s equals minus 6 minus 8j. Right? And all of these 4 roots of the denominator represent poles. So I have, these are the poles, and in the previous slides I talked about the zeros, right? So let me write these poles down in that function too. So you also get to have a function. So you're gonna get 4 times s plus 10, s plus 6. Sorry, where is it? Okay, s plus 6 minus 8j. Okay. S plus 6 minus 8j and s plus 6 plus 8j, right? And 4 cancelled out with 10. So again, these 3 are the roots of the numerator. So these 3 are the zeros, and these 3 will give the roots of the denominator. So this will represent the poles, and this will represent the zeros. Okay, so now I can easily draw them on that axis, right? Let me write the zeros over there as well, just to make my life easier. I already have the poles, so zeros were s equals minus 5 and s equals minus 3 plus 4j and minus 3 minus 4j. Okay, now let's start with the zeros. The first zero is minus 5. Again, this is s-plane, right? Over here, this is the imaginary axis, if you will, and this is a real axis. So the first one is minus 5. Here is minus 5. On the real axis, again, imaginary component is 0, so you're going to get minus 5 over here. The other 0 is minus 3 plus 4j, right? So minus 3, minus 1, minus 2, minus 3, plus 4j, 1, 2, 3, 4, right? So here's the next 0. Similarly, minus 3, minus 4j, 1, minus 1, minus 2, minus 3, minus 4. So here's a third 0. So this is how you can easily plot the zeros on the S-plane. Similarly, you can plot the poles on the S-plane as well. Again, the poles on the S-plane is one pole is 0 over here, right? These are represented by crosses. So you had a cross at 0. The next one is a cross at minus 10. Here's a cross at minus 10. The next one is minus 6 plus 8j. So minus 6 again is on this axis. 1, 2, 3, 4, 5, 6. So this is minus 6. Plus 8j is over here. And minus 8j is over here. So this is how you can plot the poles and the zeros on the S-plane. We're going to do the second part of this problem as well very quickly. Where here's our function. And we have to repeat the whole thing again. The numerator, finding the numerator roots and finding the denominator roots. And then plotting them on the S-plane. Let me see what the function is so I can write down the function very quickly first, right? Okay. So solution for the part B now, f2 of s is 8s squared plus 120s plus 400 divided by 2 times s4 plus 20s cubed plus 70s squared plus 100s plus 48. Okay, so this is good. Now let's start with numerator. Numerator is again 8. Let's first take 8 out. So I am left with s squared plus 15s plus 50, right? So 50 times 8 is 400. Okay, and I can further solve this quadratic equation by doing again s equals minus b plus minus b squared minus 4 ac over 2a. So I got the two roots as minus 5 and minus 10. Both were real. Okay, so I can potentially write the numerator down over here as taking 8 common out, and then these are the two roots. So s plus 5 and s plus 10. So this is my numerator. Okay, nice. And again, these s equals minus 5 and s equals minus 10 represents the zeros. Okay, let's do denominator. So denominator is, again, this is your denominator. I'm going to start by taking 2 out, right? Okay, so once I took 2 out, I'm left with s power 4 plus 10s cubed plus 35s squared plus 50s plus 24. Okay, now let's start with solving this s to the power 4 equation, and we can potentially solve that by getting 2 quadratic equations. So once we're going to solve them, we will get 2 quadratic equations, right? So for example, I'm going to get 2 and then 2 quadratic equations, which are s squared plus 5s plus 4 and s squared plus 5s plus 6. Okay, now the roots of this quadratic equation, s squared plus 5s plus 4, are s equals minus 1 and minus 4, and the roots of these are s equals minus 2 and minus 3, right? So minus 1, minus 2, minus 3, minus 4 are all poles. Okay, nice. So I also got these 4 roots, so, and these are the poles, so I can put them in the denominator. And again, in the denominator, I'm gonna get 2, and then 4 of these things, which is s plus 1, s plus 1, s plus 2, s plus 3, s plus 4, right? So these are the 4 poles that I wrote, and these were the numerator. Okay, and of course this will be cancelled out. And here's your again f of s equation in that format. And again, I got the zeros and the poles. I can easily plot them over here. This is again the real part of the S. This is imaginary axis, right? And interestingly, all the zeros and the poles are just on the negative axis, right? So for example, -1, -2, -3, -4, -5, 6, 7, 8, 9, 10. So let us start with the 0. I have two zeros, one on -5 and one on -10. So here's one 0 and here's other 0. And the poles are -1, -2, -3, -4. Perfect, right? So this is how you can, again, draw the poles and the zeros on the S-plane. And this is going to come in handy as we're going to learn more, right? Poles and zeros. Essentially, just imagine that this f of s, right? This f of s is coming from the circuit analysis where you have RC, RL, or RLC circuits and this differential integral equations. And you ended up converting them into the Laplace transform to get these kind of equations, f of s. So before we convert it back to inverse transform and get a time domain function, just looking at this f of s Laplace transformed versions of those, right? They can represent this kind of interesting things where in the numerator we have the zeros and in the denominator the roots of the denominator to make it zero have are called the poles, right? And they're going to have some interesting consequences. I am going to talk about that in a second, right? But you know how to find the roots and the poles. Start with a rational fraction, find the factors, play with the numerator and denominator separately, find all the factors and the roots. Once you find the factors and the roots, essentially plot them on the S-plane. Okay, so by the way, this is what I just plot for f2 of s over here. Okay. So very briefly, I am not going to go into the details, and maybe this may or may not make sense at this point, but as we're going to do more example problems, as we can do more circuit analysis, and again, the next chapter is all about circuit analysis, right? This thing is going to become much more clear on what I'm going to say, right? But if you actually look at that f of s, right, we look at that f of s is the numerator of s and the denominator of s, and we said that numerators are zeros and denominators are poles. So essentially, in terms of the, if you actually think about the poles are the values of s, right? Values of s that make denominator of s equals 0. And poles practically represent the stability of a system, represent stability of a system, or a natural mode, or representing a stability of the system. So for example, let's say if your pole is at s equals to -a, you're going to realize that once you're going to convert that into a time domain function, you're going to have an exponent component, right, with e raised to power -at. This is going to show that the function is going to decay and stable. Similarly, if your pole will be at s is equal to +a, then you're going to have a exponent, this exponent. This shows that the function is going to grow and this is unstable. Similarly, if your pole is some sort of a complex number, right, we were looking at the poles, right? So for example, minus sigma plus minus j omega, then you're going to realize that you're going to have e raised to power minus sigma t plus cos of omega t. You're going to get this cosine term. And what does the cosine term tell us in terms of our responses, right? It is going to have an oscillatory response. The cosine, or the presence of a sine or a cosine, is it's an oscillation, and the presence of e raised to power minus sigma t is it's a damped oscillation, right? So it's a damped oscillation. Similarly, if you're going to have a pole at s equals to, for example, just on the j-axis, on j omega, right, where sigma equals to 0. If sigma is equal to 0, for example, then we're going to realize that we are just going to have a cosine term without an exponent, and the cosine term without an exponent means as you're going to have a sustained oscillation. So the point is that this function f of s that actually came out, for example, in our cases from the circuits, The denominator of that is going to represent the poles, and what we can potentially see is that this denominator is what's introducing these terms, these exponents and cosines and the sines, and this is gonna what is going to determine the stability of a system in terms of whether it's going to decay or grow or have a sustained or damped oscillation. Very quickly, zeros, right? Zeros is again, zeros what makes the n of s, the numerator of a function, to be zero, right? And if the numerator of the function is zero, your f of s will become zero. So another concept that again the physical explanation of the pole and the zero is going to become much more sense when we're going to go through the entire next chapter, right? So just bear with me over here for another couple of weeks on this point. But having said that, we're gonna learn about the transfer function as well in the next chapter. And transfer function is usually your output, right, over input, right? So for example, your y of s over x of s. And again, y of s can be your numerator over here, and x of s can be your denominator over here. And so transfer function represents the system response in terms of what is the output divided by what's the input is. And practically, what we are going to realize that the zeros is what kind of filters or blocks certain behaviors, right? So zeros, the presence of the zeros, right? You can call it as how the system filters or blocks or attenuates certain behavior. This is going to become also much more clear when we're going to move beyond Laplace transform the circuit. The Laplace transform is going to start talking about the filters as well. But anyhow, in short, if you want to remember something today, just remember that the poles and the how to calculate poles and the zeros, how to plot them in the S-domain, and they have a very important function. Poles represent the stability of a system, and depending on where the poles are, right, your system can be stable or unstable. And zeros represent how the filter attenuates certain things out in terms of its response. We're going to look more about the zeros and the poles. Another important thing that kind of a take-home message, specifically in terms of the poles, right, because they are representing the stability in all of these exponents, that the poles ideally should be on the left-hand side of the S-plane, right? It should have a minus a, or it should have a minus sigma over here, which is minus a. You can still call it minus a. Having poles on the left hand side will ensure that you're going to have a stable system where right, where it is gonna die out eventually. For example, in terms of a natural response, right, once you store energy in the capacitor and the inductor, right, and you take the energy source out, those systems should die out and not oscillate, which is known, but yeah. Okay, so with that, we're going to kind of finish this lecture, this part of the lecture. In the next lecture, we're going to talk about the next thing. All right, thanks, bye.